In this video, we will introduce you to the implementation of requirements for Team 8's Leo rover equipped with a robotic arm. In the design phase, we envisioned the requirements to be divided into three major categories, each containing our detailed subdivision requirements. The overall status of requirement fulfillment is shown in the diagram. Finally, we will introduce our team members and their respective responsibilities. In target recognition, we rated the recognition of green light as green, capable of identifying up to two objects simultaneously and recognizing 9 different shapes and sizes of block with an accuracy rate of 20 out of 20. In the evaluation of target grasping and object grasping capability, we assigned an amber rating due to the issues observed in testing, such as the simulation of the grasping mechanism, acting contrary to the reality and inability of the robotic arm to grasp object below its horizontal plane. Virtual grasping achieved 100% of success in tests under the assumptions that on the Leo rover objects are placed on the ground, and actual grasping occurs on a flat surface with grasping mechanism functioning normally. The manipulator placed blocks in specific position with 90% success rate on the first attempt. This rate accounts for occasional block movement or toppling of narrow upright blocks. Target recognition using a depth camera achieved an 80% success rate. Analysis of unmet requirements is as follows. One is a motor power problem and the second one is an arm gripper issue. Regarding the capability of re-attempting grasp after failures, we rated it as amber because of the instability. Due to the instability of the grabbing clip, which resulted in inability to perform the grabbing operation, henceforth we had to rate it as amber. In error reporting, we assign a green rating as errors were mostly reported accurately. In actual testing, our battery demonstrates the capability of repeated charging. Users can query the voltage value of Leo rover battery and determine if it's in a low battery state via the command line interface. The battery can sustain stable operation of the radar and Leo rover for over 30 minutes. However, it falls short of the expected 2-hour endurance. Additionally, the power supply for NUC mechanical arm and depth camera is achieved through the use of extension cords and power strips connected to an external power source rather than Leo rover's battery. Consequently, the robot can execute 15 minutes of mobile and grasping tasks. Moving on to mapping and navigation, the process begins with the deployment of various sensors on board the robot, including LiDAR and IMU. These sensors work in tandem to collect environmental data and the robot's state information. This raw sensor data is then fed into a SLAM algorithm installed on the robot. With SLAM Toolbox, we utilize advanced techniques like Kalman filters and IMU filter manual to process the sensor data and estimate the robot's position and orientation in real time. Our method involves comparing the map generated by the robot with the accurate map of the known environment at least 3 times to check for discrepancies. As you can see in this video, the SLAM data is generated and accurately mapping the environment, providing the robot with a comprehensive understanding of its surroundings. We've achieved 100% accuracy in simulation environments owing to the rigorous testing and optimization. However, in real-time scenarios, our accuracy currently stands at 50%. While our system generally meets the requirements, there are instances where the real-time simulation did not occur properly. The reason behind this issue is the failure of TF to receive odometry filtered data properly in real time, which impeded our ability to conduct real-time testing. Now, we'll explore how a robot successfully navigates to predetermined targets in different environments. The robot consistently achieves its objectives by accurately arriving at or near the predetermined target location with an error margin well within the predefined acceptable limit of less than 10 mm. This precision is facilitated by our meticulous identification of target points through color thresholds, ensuring reliable recognition even when varying environmental conditions are present. Once identified, the robot seamlessly executes global path planning algorithms. While our simulation accuracy remains consistently high at 100%, real time navigation encounters discrepancies that challenge the system's performance. Our robot demonstrates the capability to navigate in real time. It does so with the occasional interruptions that prevent seamless operation. In ideal conditions, our system successfully processes real time data from various sensors, enabling the robot to dynamically perceive its environment and adjust the navigation accordingly. The real time operation may not occur properly when the system fails to receive odometry filter topic data from Kalman filter effectively. This impacts the precision of real time navigation, leading to deviations from the intended path. Due to unreliable odometry filter data, our system lacks crucial feedback for informed path planning and trajectory adjustments. Consequently, the robot may become off course, experiencing overshooting, undershooting, or erratic movements. Despite efforts with OpenCV for target point detection, environmental factors like lighting variations limit its effectiveness. This leads to challenges in accurately identifying target points, causing deviations from the intended path. In each of the four experiments, we systematically adjusted key parameters such as inflation, obstacle layer values, and resolution settings. First, we explored the effects of inflations on robots' path planning. Next, we delved into obstacle layer values. These adjustments were crucial in fine tuning robots' perception and its environment, ensuring accurate obstacle detection and avoidance. Finally, we experimented with resolution settings, refining granularity of our map representation. We meticulously crafted a series of 10 experiments, ensuring consistency by maintaining the target position across each trial. What emerged from these experiments was, while our simulations remained accurate, consistently falling within the acceptable range of 10 millimeters from the target object, the reality of real-time navigation painted a different picture. Here we encountered fluctuations with measurements typically exceeding 20 millimeter from the intended destination. Through parameter tuning, we witnessed a noticeable increase in accuracy. Here we have RQT graph showcasing the flow of data within our system. As you can see in the Leo rover's topic, wheel odom with covariance is being subscribed by EKF mode along with its IMU data, and it's publishing odometry filter topic to the transformations. Despite receiving and processing odometry values correctly, there seems to be a discrepancy between the expected and the actual movement of the robot. For obstacle avoidance, we have successfully completed our first phase of the verification process by placing obstacles in the robot's path and closely observing its strategies. We have conducted a series of 10 experiments. Each experiment involved varying obstacle placements to ensure utmost accuracy in our system's performance. The simulation was working with 100% accuracy. We carefully crafted 4 experiments, each centering on obstacle avoidance with distinct obstacle position. In each experiment, we meticulously conducted 10 trials, monitoring collision occurrences. And through the rigorous parameter tuning at each stage of our experiments, we observed a significant reduction in collisions within our simulation environment. However, despite these optimizations, we noticed a persistently high collision rate in real-time environments. The unmet needs stem from the challenges encountered during NAV2 parameter tuning. Despite our efforts, the parameters governing the navigation system could be more sufficiently optimized to meet the desired performance standards. Our implementation relies on Leo rover's user interface, accessible via web browser leveraging ROS Live and ROS Bridge for seamless communication with ROS topics. Users can effortlessly control the robot using keyboard or virtual joystick with the TwistMux node and coordinating with and arranging different motion commands as per the user's instructions. In conclusion, while our journey has presented its share of challenges, it has also illuminated pathways for growth and innovation. Through diligent experimentation and analysis, we have uncovered invaluable insights that will guide our future endeavors with a steadfast commitment to refinement and optimization. We are poised to elevate our system's performance and redefine the possibilities. Thank you.